Hello everybody and welcome back to the second video of a series of two here where we're trying to convert between polar coordinates and Cartesian coordinates. This time around we're going the route from Cartesians to polars. So to do that route we have to use the information that we had from the previous video and massage it a little bit so we get some new expressions going. Specifically here, if we add together the square of x and the square of y, according to their definitions right here, we would get r squared cos squared theta plus r squared sine squared theta. And we can factor right now the r squared in order to get in the bracket cos squared plus sine squared theta. And we know from an identity that this is very well equal to 1, the whole expression here. So we've essentially derived that x squared plus y squared is basically the size of r squared. That's our first bit of information. And then we need one more. So how do we get the one more? We can go and compare right now y against x. According to our definition, y is r sine theta and cos is r cos theta. The r's here will drop immediately, while the sine over cosine actually will get us a tangent function right now. And in fact, I can use basically this tangent function. I can invert it on the other side to get my theta if I wish to. Now, I should mention that the top equation is typically written in this form, but it's going to be useful in this form because essentially we're trying to find the r component, right, in our polar coordinates. So we're going to have to square root both sides here. I know that you're thinking there must be a plus or minus here, but r cannot be minus in the polar coordinate system. There is no r. The size of the vector here, sizes of vectors cannot be negative. So even though there is a negative technically there, it's unphysical for the coordinate system we're in. Sizes of vectors, again, can't be negative. Okay, so this is pretty much equation 1. And below is the other one that will determine our theta component. Very simple stuff. So we'll take what we learned here and we'll apply it again to 3 examples that are, very characteristic. Let's go and attempt them. Here they are. We're trying to convert the following points from their Cartesian, again, representation to the polar one. And let's see what we got. Before I attempt any of them, first thing, again, I advise you is to use a plot of the unit circle. You can't attempt these questions without it. So we got here an x of 1 and a y of 0. It basically means we're hanging out somewhere over here, as you can see. Now, because I have my, unit circle in place, I can very easily see, without using any equation right now, that the r vector has no choice right now but be exactly of size 1. And our theta angle, since we're touching the positive x-axis right now, is literally nothing more than 0 radians, or 0 degrees. So my answer immediately, I'm not going to use any equations. I'm just going to say the point right now in polars is simply 1, 0. And that's the end of it. You can use equations if you want to prove it, but I've done it with just looking at the diagram. And if you're writing an exam or an evaluation, you probably want to be as fast as possible. So that's why I encourage you to draw diagrams all the time. Now, for the other one, it might not be so obvious because this time around, we're hanging out at an x value of root 3 and a y value of 1, it seems. So again, our point is at the intersection of these two, right there. And we will connect it again to our origin with our r vector. So we don't know yet what the size of this r is going to be. We know we're in the first quadrant though, and we're searching for that theta. Okay, so I can obtain r very easily by doing again Pythagoras on the two components. So adding 1 squared along with root 3 over here squared itself, which would get me basically root 4 or just 2. That's very easy, and we can move on from here to do our theta with how we've learned through the inverse tangent of the y component over the x component. And the actual y component right now is, let's see here, 1, and the x component is root 3. Now, this is, again, a special triangle that we're dealing with. It's the 30, 60, 90, it seems. Okay, against the 30 degrees is the 1, against the 60 degrees is the root 3, and the hypotenuse is 2. Okay, so if we have a tangent of 1 over root 3, it means again that the opposite side is 1 and the adjacent side is root 3. The guy that has these right now in our special triangle, opposite of 1 over adjacent of 3, is our 30-degree angle. So this ends up giving us, specifically here, pi over 6. All right, and we know we're in the first quadrant. We don't have to really think about this theta much longer. We basically have the point in our hands. We can compile the information here. The size of r is 2, and the angle is pi over 6 with respect to the x-axis. And we're good to go. No more worrying. So this is typical, a typical setup over here. And then in the next example, we make it a little bit harder by driving us away from the first quadrant. Now we're hanging out somewhere over here at -1 and a -1 in the y as well. So our r vector we know is going to go like this. Okay, it's going to connect us again to the intersection of these two lines. I'll try to make it nicely drawn like that. So this is where our point of interest is. And again, this time around, notice that the solution right now, the theta, is this big old angle from the x-axis. That's what we're trying to find. But we also have a smaller angle, I'll call it phi over here, that I could also determine because I have the side lengths of this right angle triangle. If you pay close attention, this side length here, for example, is just 1. And this side length here is also 1. So basically right now, I could find phi, you can very easily tell, by doing tan inverse of 1 over 1, that phi here is going to end up being just pi over 4, or 45 degrees. And now that I have that in my hands, I can find theta by thinking how it's related to phi. So this angle over here right now would have been pi, but we have to add our phi angle to get to the actual solution. So if we want theta, we got to take 180 degrees and add phi to that. So in total here we have pi plus pi over 4. If we bring them to a common denominator, 4 pi plus pi over 4, or 5 pi over 4. There we go. As for the r, it's still very straightforward to get. We can get it by putting our coordinates here and add them in quadrature using Pythagoras. And we see here that we're just going to get root 2 for that one. So we've got both the angle and the size of r right now, r again being this guy, the size of that red vector. And we can put it all together to finish off our question. So the actual polar coordinate version is root 2 and then 5 pi over 4. That's the end of the story. We can see again in the first part how easy it was to just tell what the polar representation is going to be. No equations necessary. The second one's a little more involved and very typical. And the third one was even more involved because you had to think of theta being a composite angle, and you had to determine phi before you could determine theta. But those are pretty much the three typical scenarios you find in converting these angles. And again, if you now understand a little bit better how to convert between your Cartesian representation and your polar representation, consider again subscribing. Thanks for watching.